These are the notes for Learning Target 3.3, which says I can solve problems using balanced forces, or the net force is equal to zero, which is another way to say balanced forces. Newton's first law states that an object in motion will stay in motion unless acted upon by a net force. Additionally, an object at rest will stay at rest unless acted upon by a net force. And so, for example, if we want this shopping cart to speed up or slow down, we need the forces acting on it to be unbalanced. And so in this case, the person is pushing with a stronger force than the friction is providing, and therefore those forces are unbalanced, which will mean that the shopping cart will change velocity, it will speed up. The opposite case is if the forces acting on something are balanced, like shown in this picture, then the object will stay at a constant velocity. And this means that if it's moving, it'll continue moving at the same velocity, or if it's at rest, it'll continue being at rest. So for our first example on your notes, we have two people that are pushing on the same shopping cart. So you can go ahead and draw this force diagram next to this picture on your notes. And while you're drawing it, you can see that the forces in the x direction are balanced, meaning that the force that person A is providing, pushing to the right, is equal in magnitude to the force that person B is pushing to the left. And since these forces are equal, that means that the shopping cart's velocity won't change. So if the shopping cart started at rest, it will continue to stay at rest because these forces are balanced in the x direction. The second sentence at the top of the slide says consider horizontal and vertical forces separately. And that is important because the vertical forces here are also balanced with each other, which means that this shopping cart will not change velocity upward or downwards. It will stay at rest vertically as well as staying at rest horizontally because the forces are balanced in the horizontal and the vertical direction separately. The second example on your notes is for this person pushing the shopping cart, and so you can see that they are moving. But as you draw this force diagram, you'll notice that it's very similar to the force diagram on the previous slide, and that is because the amount of normal force provided by person A on the cart is equal to the amount of friction force felt between the cart and the ground. And so because these forces are balanced, once again, this cart is going to have a constant velocity. But since the cart is already moving, that doesn't mean that it's going to stay at rest. It means that it's going to stay moving at the same velocity that it was moving at because it has balanced forces acting on it. So if you have balanced forces, you can either have something at rest or moving, but either way, the velocity will be constant. It's not going to be speeding up, slowing down, or changing direction. For the first example, we have a 2 kilogram textbook that sits at rest on a table. What is the normal force that acts on the book? So we're trying to figure out what is the magnitude or the size of that force. Because this book is at rest, we know that the forces must be balanced. So the upwards force has to be equal to the size of the downwards force. And so the downwards force, the gravitational force, has an equation from Learning Target 3.2, which we can use by multiplying the mass of the book times the acceleration due to gravity of 9.8 meters per second squared. We can find that there are 19.6 newtons of force pulling the book downward. And so because this book is at rest, we know that the same amount of force must be pushing up on the book from the table, which means that the table is providing 19.6 newtons of force upwards. So this is the answer. Example 2 has 3 parts. So this consists of a shopper pushing a 20 kilogram cart using 40 newtons of force. They are moving at a constant velocity, and the first part asks us to determine what is the amount of friction force between the cart and the ground. So with this picture, here's a force diagram. I'm going to take the picture out so it is a little bit clearer to see. And so we know that the person is pushing with a force of 40 newtons. And we also know that this cart is moving at a constant velocity. So because it's moving at a constant velocity, we can say that the friction force and the normal force from the person are going to be equal to one another because the net force in the x direction is 0. What this means is that if we look at the x forces that there's not going to be any unbalance between them. They're going to be balanced. Another way to write this is that the friction force is equal to the normal force, and that's by adding friction force to both sides. So because we know that the friction force is equal to the normal force, and the normal force is 40 newtons, we can then say with confidence that the friction force must be the same size. It has to be 40 newtons to the left to balance out the 40 newtons to the right provided by the person. And so this is the answer to part A. For part B, it says to determine the normal force provided by the ground. And so for this, we can assume that the normal force is going to be balanced with the gravitational force. And so we'll use the same thing that we did with the textbook, same equation to find that the gravitational force is 196 newtons. And then we'll use this statement, which says that the y direction forces, the vertical forces, are balanced, which means that the normal force and the gravitational force are equal to one another. And so because we know that the gravitational force is 196 newtons, then the normal force must be the exact same size, but pointed upward. And then the third part of this example actually doesn't have to do so much with balanced forces, because we've already figured out the size of all the forces because they were balanced. But this is just going to be a quick review of one of the equations that we used in Learning Target 3.2, which says that the friction force is equal to the coefficient of friction times the normal force. And so here we have the friction force is 40 newtons, the normal force based on the same object. So we're looking at the cart and the ground here. So that normal force is 196. And if we divide both sides by 196, we get a coefficient of friction of 0.204. Remember that coefficients of friction do not have units. And thank you very much for watching.